Hello everyone, here in another session on stereochemistry discussion, we are seeing optical isomerism. We will see various optical isomers, optical activity and different conventions of denoting the configuration of optical isomers. So to begin with, let's see what is optical activity. Optical activity can be demonstrated like this. Here you've got a light source, and when light is emitted from the source, you can see there the electromagnetic wave oscillates in all directions in the given plane. And if you place a substance called polarizer is placed in the pathway of the light, you can see there the light which is passing through the polarizer passes the oscillation only in one direction. And that phenomenon is called polarization, plane polarization. That is, oscillations in all the directions are restricted now to the given direction. And now this plane polarized light, if you pass it through an optically active substance, you can see there the substance can rotate the plane of polarization through certain angle. And such substances are therefore called optically active substances because they can rotate the plane of plane polarized light through certain angles. Optical activity is the ability of compounds to rotate the plane of plane polarized light, and the isomers with different optical activity are called optical isomers. That is, they possess the same molecular formula and structural formula, the same connectivity, but their optical activity is different. The ability of the substance to rotate the plane of plane polarized light is measured through specific rotation. Alpha is given for a constant wavelength of light and for a given temperature as the measured rotation alpha with respect to the concentration and path length. A molecule is optically active if it possesses a condition called chirality. That is, the molecule should have at least one carbon which is attached to four different substituents or four different groups. Like this. Here, the carbon in the middle is attached to four different atoms or groups, and here in the other case, this carbon is not attached to four different groups. The two substituents are the same here. And what is the difference between those two compounds is that if you cut the first molecule through this plane, you can get two unequal halves. Whereas if you cut the second molecule through the same plane, you get two equal halves. So the first one, the chiral molecule, is not cut into equal halves, whereas the second one is cut into equal halves when it is cut along the plane of symmetry. So the chiral molecule do not possess a plane of symmetry, whereas the achiral molecule possesses plane of symmetry. And that carbon which is attached to the four different groups in the chiral molecule is called chiral center or chiral carbon. So for a molecule to be optically active, the most important condition is that it should possess a chiral carbon, at least one chiral carbon. And there are two types of optical isomers, enantiomers and diastereomers. Let's see those two cases. The two structures are related as mirror image of the other one. If the second structure is seen in the mirror, you get the first structure. And if you try to superimpose the two, you get something like this, that is, they are not superimposing. So the two structures are related as object and its non-superimposing mirror image. The superimposability can be understood with these two examples. Here you have got the English alphabet H. The letter H and its mirror image are superimposable. On the other hand, the letter P and its mirror image, they are not superimposable. So enantiomers are two optical isomers which are related as object and its non-superimposing mirror image. Now let's see another two structures like this. They are not related as object and mirror image. Such optical isomers are called diastereomers. Coming to enantiomers in detail, they have same connectivity but opposite three-dimensional structure, therefore opposite optical activity. When plane polarized light is passed through the first one, you get a rotation of the plane of polarization to a certain angle, to right here in this example through theta angle. On the other hand, the other compound rotates the plane of plane polarized light through the same value of angle but in the opposite direction to the left. So the enantiomers rotate the plane of plane polarized light in equal magnitudes but in opposite directions. And the one which rotates the plane of plane polarized light to right is called a dextro-rotatory isomer, whereas the other one which rotates the plane of plane polarized light to left is called levo-rotatory. And diastereomers, they have same connectivity again but different three-dimensional structure, not necessarily opposite, and possess different optical activity. These two molecules, the first one rotates the plane of plane polarized light, for example through right by an angle theta degree, whereas the second one rotates the plane of plane polarized light through another angle phi degree, that too in the opposite direction to the left. These two are related as diastereomers. So the two diastereomers shown here can rotate the plane of plane polarized light in opposite directions and in opposite magnitudes. It can also be that the second isomer rotate the plane of plane polarized light in the same direction as the first one but in different magnitudes. So diastereomers are optical isomers which rotate the plane of plane polarized light in different magnitudes and in different or same directions. Let's now see an example of lactic acid. Here is the structure of lactic acid. It possesses one chiral center, the carbon in the middle here. If it possesses one chiral center, the number of stereoisomers possible are 2 to the power 1. That is, lactic acid possesses 2 stereoisomers. So the structure of the second isomer will be like this. And on a closer look, it can be seen that the two structures are non-superimposing mirror images to each other. That means they are enantiomers. On measurement of optical activity, it was seen that the first enantiomer is a dextro-rotatory lactic acid. That means it rotates the plane of plane polarized light towards right through an angle of 2.67 degree. And the second structure is measured to be levo-rotatory with a specific rotation of minus 2.67 degrees. So the two optical isomers of lactic acid are enantiomers. And what could be the optical activity if you have the dextro-rotatory lactic acid and levo-rotatory lactic acid in the same amount? That means an equimolar mixture of dextro and levo isomers will be optically inactive because optical activity due to the dextro isomer is cancelled by the optical activity of the levo isomer. Therefore, an equimolar mixture of the two will be optically inactive, and such mixtures are called racemic mixtures. And coming to glyceraldehyde, here is the structure of glyceraldehyde. Again, the compound possesses only one chiral center as shown here. Therefore, it possesses two optical isomers as shown like this. They are related as object and non-superimposing mirror image. Therefore, they are enantiomers. And the first one, the dextro-rotatory glyceraldehyde or D-glyceraldehyde, D and L here should be in small letters. The dextro-rotatory glyceraldehyde rotates the plane of plane polarized light through plus 87 degree, whereas the other one, the levo-rotatory glyceraldehyde, rotates the plane of plane polarized light through 8.7 degree but to the opposite direction towards the left direction. And an equimolecular mixture of the dextro and levo isomers will be optically inactive, will be a racemic mixture. And coming to tartaric acid. Tartaric acid here has got two chiral centers, the first one here and the other one over there. And therefore, the total number of isomers, the stereoisomers possible are 4, that is 2 to the power 2. And these are the 4 different optical isomers of tartaric acid. Among these 4, the last 2 are identical in structure. So we will consider only 3 structures in the further discussion. Considering the first 2 structures, the green and blue one, they are related as object and non-superimposing mirror image. Therefore, they are enantiomers. And the first one is dextro-tartaric acid. It rotates the plane of plane polarized light through plus 12 degrees, whereas the second one, the blue one, is levo-rotatory tartaric acid with a specific rotation of minus 12 degrees. And let's now consider these two pairs. Here you've got the levo-tartaric acid, and if you compare the L-tartaric acid with the other structure, you can see that they are not related as object and mirror image. That means they are diastereomers. And the diastereomer shown here is called meso-tartaric acid. it has got a peculiarity that it possesses a plane of symmetry. That means if you cut the molecule through this particular plane, you can get two equal halves. Such a molecule will be optically inactive, although it possesses two chiral centers. And the optical inactivity arises due to internal compensation. That means optical activity due to the lower half of the molecule is cancelled by optical activity due to the upper half, and therefore meso-tartaric acid is optically inactive due to internal compensation, and hence the specific rotation will be 0. So meso-tartaric acid is a special case where the molecule is optically inactive although it possesses two chiral centers. Now comparing this pair, let's see how they are related. The first one is dextro-tartaric acid and the other one is meso-tartaric acid, as we have seen before, with a specific rotation of 0. And these two are again not related as object and mirror image, hence they are diastereomers. So that's about the optical activity in tartaric acid. You have got dextro-tartaric acid, levo-tartaric acid and the meso-tartaric acid. The dextro and levo-tartaric acids are enantiomers to each other, whereas the dextro and levo-tartaric acids are diastereomeric to the meso-tartaric acid, and the meso-tartaric acid is a special case of having plane of symmetry and hence optically inactive due to internal compensation, although it possesses two chiral centers. With that, we are done with the introductory part of optical isomerism, and now let's see different conventions used to denote the configuration of optical isomers. And here is the relative configuration, which is also called DL configuration. Here in the relative configuration, the configuration of the given molecule is related to the configuration of glyceraldehyde molecule. That is, glyceraldehyde is taken as an arbitrary standard. Here, the first form is arbitrarily assigned as D-glyceraldehyde and the second one as L-glyceraldehyde. Then for a given molecule, you need to look at the chiral center. If it possesses more than one chiral centers, you need to look at the second last chiral center. So configuration at that particular chiral center, if it matches with that of the D-glyceraldehyde, the molecule is possessing D configuration. Whereas if the configuration at the chiral center matches with that of the L-glyceraldehyde, the configuration will be L. So here you have got D and the L configuration based on the relation to the D and L glyceraldehyde. Actually, the D and L configurations of glyceraldehyde are assigned arbitrarily, but later with the invention of X-ray crystallography, it was found that the dextrorotatory glyceraldehyde possesses the configuration the D-glyceraldehyde and levorotatory glyceraldehyde possesses L-glyceraldehyde configuration. So here in case of glyceraldehyde, the dextro notation and the configuration D matches, but in general the DL configuration is not related to the optical activity dextro or levorotatory. The capital DL is the configuration which is assigned based on the structure, the three-dimensional orientation of atoms or groups about the chiral carbon. On the other hand, the small d and L, the dextro and levo are assigned based on the measurement of optical activity of the molecule. So in general, the DL configuration and the dextro-levo isomers are not related. And now let's see the absolute configuration, or S configuration, proposed based on Can-Ingold-Prelog sequence rule. The three scientists proposed several rules to find out the R and S configuration. Let's see it through a demonstration. Here you've got a molecule where a chiral carbon is attached to 4 different groups. In the first step, to assign R or S configuration, you need to prioritize the substituents according to the atomic number. That means the atom which is directly connected to the chiral carbon are numbered like this. Here among all the 4, you've got bromine with the highest atomic number, so it possesses the highest priority, and then comes chlorine, and then comes hydroxyl group because here oxygen is directly attached to carbon, and the last priority goes to hydrogen. And there are special cases. If you've got a double bond, the double bonds are treated as separate single bonds like this. And if you have got isotopes attached like hydrogen and deuterium shown here, the heavier isotope is numbered with higher priority than the lighter one. And if you've got two substituents with the same atom directly attached to the central carbon atom, like here chlorine gets the first priority, and if you look for the second priority, you can see that these two groups possess carbon which is directly attached to the chiral carbon. In that case, you need to look for the next atom which is attached to those two carbons. So here in this case, the carbon is attached to another carbon with the highest atomic number, whereas in the aldehyde group you can see that the carbon is attached to oxygen which is even higher in atomic number. So the next priority will be going to the aldehyde group than this alkyl group, and then hydrogen possesses the lowest priority. Always if you have got hydrogen attached to the chiral carbon, hydrogen atom possesses the lowest priority. So likewise, based on this kind of rules, you can number the substituent atoms or groups, and after numbering, you should bring the lowest priority group to the back side, or in the Fisher projection to the lowest vertical part. In order to bring this lowest priority group hydrogen to the lower part here, you need to exchange this lowest priority group here with the hydroxyl group. So for this exchange, you get a new structure like this, and remember, with a single exchange, the new structure obtained is having opposite configuration to the original structure. If you want to get the identical structure to the original structure, you need to make two exchanges. So now when your lowest priority group is at this bottom vertical part, you can exchange among any pair of the three. So here I make an exchange between those two groups here. So my new structure is something like this. And now after having these two exchanges done, the third structure here is identical to the original or the first structure we started with. And now what you need to do is you need to look at the other substituents from the side of the fourth priority group, that is from the side of the hydrogen here. If you look up with your eye going from the first priority to the second priority and then to the third priority like this, and if your eye moves in the clockwise direction, such configuration is called R configuration for the word rectus, meaning right. And on the other hand, if you've got this structure and you prioritize the substituents like this, and in order to bring the fourth priority hydrogen here at the bottom vertical part, you make an exchange like this, and the resultant structure possesses the opposite configuration to the first structure. Therefore, you make one more exchange. I exchange between those two groups, bromine and hydroxyl groups, and so I get this new structure here. And looking from the side of this fourth priority group hydrogen, from 1, 2, 3 groups, my eye moves in anti-clockwise direction, so I possess S configuration for the word sinister, which means left. So this is how you assign R or S configuration to an optical isomer. And remember, always the first structure, if you're doing single exchange between groups, you get opposite configuration. That is, the structures 1 and 2 are possessing opposite configurations here. And if you do two exchanges, that means structure 1 and 3 are having identical configuration. Likewise, structures 2 and 3 are opposite in configuration because 2 and 3 are related just by single exchange. Let's now see the example of lactic acid. Here you've got the levolactic acid and the dextro one. Prioritizing the substituents on levolactic acid, the hydroxyl group possesses the highest priority because oxygen is attached to carbon here directly. For the carboxylic group and for the methyl group, in both the cases you've got same atom attached on the chiral carbon. So we need to look for the second atom. Here for the carboxylic group, the next atom is oxygens, 2 oxygens, and here the next atom is hydrogens only. So the second priority goes to the carboxylic group, and then the third priority to the alkyl or the methyl group, and then hydrogen gets the fourth priority. Now the next step is to bring the hydrogen down here with an exchange between the methyl group and the hydrogen. You need to do one more exchange to make the new structure identical to the original structure. So Here I selected exchange between these two groups, the methyl group and the hydroxyl group. You can also select between methyl and carboxylic or carboxylic and hydroxylic, whatever. So with this exchange I get new structure like this, and from the side of hydrogen, if I look from 1 to 3, my eye travels like this in the clockwise direction. Therefore this configuration is R lactic acid. So levolactic acid is R lactic acid, to say its absolute configuration. And the dextrorotatory lactic acid, if you can number like this, and to bring the hydrogen from this position to the vertical down position, you can make an exchange between those two, the methyl group and hydrogen, and the new structures like this. And to get the structure identical to the original structure, you need to make one more exchange. I opted between those two groups, the methyl and carboxylic groups. So I've got new structure like this. After the two exchanges, my priorities are positioned here, and when I look from 1 to 3 direction, my eye moves along the anti-clockwise direction. Therefore the configuration is S. That means dextrolactic acid is S-lactic acid. So you can say that the levo and dextrolactic acids, the two enantiomers, are possessing opposite absolute configurations. And now we have got a case of tartaric acid. The peculiarity of tartaric acid is that it possesses two chiral centers. And according to the IUPAC nomenclature system, you can number the carbons like this, and the second and third carbons are the chiral carbons. Here you need to mention the absolute configuration at each carbon. So what you need to do is consider the first chiral center, that is the second carbon here, and prioritize the groups attached around it. Here you've got hydroxyl, carboxylic, hydrogen, and this whole group as the fourth substituent. So you can prioritize among these four substituents, and by following the steps as described previously, you can see that the second carbon here, this chiral center is having R configuration, and in the same way you will get that the third carbon is also possessing R configuration. That means the configuration of dextrotartaric acid is 2R, 3R, meaning that the second and third carbon, both chiral centers possess R configuration. And in the same procedure, you will see that the levotartaric acid possesses S configuration on both its second and third carbons. And mesotartaric acid is possessing 2R3S or 2S3R configuration if you check. And from that, the dextro and levotartaric acids are oppositely related in terms of absolute configuration, and you can see the relation of dextrotartaric acid with the mesotartaric acid there. At one chiral center, the configuration is different. Comparing levotartaric acid and mesotartaric acid, the configuration at the second carbon is different. And that's all about the introductory part of optical isomerism, optical activity, optical isomers, enantiomers, diastereomers, different examples, and how to denote the configuration of optical isomers in absolute method and in relative method. And in the next session, we will continue with the optical isomerism, wherein we will discuss resolution, racemization, enantiomeric excess, etc. Thank you.